Hello, my name is Mengyu Fu. This work is a collaboration of University of North Carolina and Israel Institute of Technology. Automating medical procedures using robots has the potential to improve patient care by enabling procedures with greater precision, accuracy, safety, and speed. Motion planning that automatically computes motions for robots to accomplish medical tasks is critical for automation. But automation cannot be trusted and widely adopted unless motion planning is certifiable, which means there are guarantees on the performance. In this work, we focus on a steerable needle medical robot and introduce a motion planner that offers a form of completeness guarantee, resolution completeness. Needle-like devices are widely used for procedures like biopsy and therapy delivery. Medical steerable needles are highly flexible so they can follow 3D curvilinear trajectories inside tissue. Such ability to steer around anatomical obstacles help us to reach previously inaccessible sites in the body. Motion planning for steerable needles calls for computing a 3D trajectory that complies with needle's kinematic constraints, avoids all anatomical obstacles, and precisely reaches the target site. To the best of our knowledge, no existing motion planner for steerable needles provides completeness guarantees. Here, we provide resolution completeness. Generally speaking, a resolution characterizes the discretization of some motion-related space. A planner is resolution complete if there exists a fine enough resolution with which the planner finds a plan in finite time when a qualified solution exists, and otherwise correctly returns that no such plan exists. For a real-world system, it is reasonable to assume there exists a resolution that describes the smallest interval or precision of achievable motions, limited by physical hardware. There are three major parts in this work: carefully designed motion primitives, a multi-resolution planning framework, and a set of domain-specific optimizations. With these three parts, we create an efficient and resolution-complete steerable needle planner. In our case, the configuration of the needle tip is in SE3 space, including 3D translation and 3D orientation. From a given configuration, we first rotate the needle around z-axis for delta theta angle, and then insert it for delta L length. Together with the curvature of the trajectory, a motion primitive is defined. By repeatedly applying motion primitives to existing configurations, we can build a search tree to explore the configuration space. We can then characterize the resolution of a motion primitive by its arc length and curving direction, and we get a set of different motion primitives. There are two extreme ways to use these motion primitives. One is exploring all resolutions when expanding a node. On the other side, exploring a final resolution only when a coarse resolution is already fully explored. Both ways have their own limitations, so in multi-resolution planning, we aim for something in the middle that allows us to use fine resolutions locally when exploring a coarse resolution. Read the paper for more details. Finally, we improve the efficiency of the planner without hurting its resolution completeness. We evaluate the planner with simulation experiments in a scenario of lung biopsy, where the objective is to deploy a steerable needle through a bronchoscope and steer from a start configuration at a bronchial tube to a target nodule in the lung parenchyma while avoiding these anatomical obstacles. We can see the example plan precisely and safely reaches the target nodule. We first compare the performance of RCS, the proposed method, with an RT-based planner. The horizontal axis is running time, while the vertical axis is success rate, which is the ratio of solved cases among all 500 test cases. This shows how success rate changes with more running time. We also have parallelized versions for both methods. Even the single-threaded RCS outperforms the multi-threaded RT-based planner. We also compare our method with an adaptive fractal tree planner. Read our paper for more results. The experiments show our proposed method, unlike the other methods, does offer guarantees on a type of completeness and also outperforms the other methods in success rate and speed. Our code is now available on GitHub. Thank you for your time.